Welcome to my channel, dear students and all the viewers. Here is the problem of a challenging problem, that is 0 to infinity integral dx over within the first bracket, that is k square plus x square, and another particular factor is k to the power n plus, sorry, this is x to the power n. Okay, so this is your x to the power n. Okay, now solving here by the some technique. First let us assume let, and this is as a I, and let us assume the variable x is equal to, that is 1 over y. So if we differentiate, then dx is equal to minus 1 over y square, and this is dy, and this is dy. Okay, so substitute here. So that is equal to 0 to, if we put here 0, then you got here infinity, and if we put infinity, then you got here 0. In that case, dx is equal to 1 over y square, and this is dy. Okay, and this is k square plus x means 1 by y square, and k to the power n plus x means 1 over y, so 1 over y to the power n. Okay, here is minus, so changing the limit here, and this is 0 to infinity, and this is dy. Take LCM y square and balancing by y square is cancel out, so we got here ky and whole square and plus 1, and another factor, if we take LCM, then y to the power n here, and this is here ky to the power n plus 1. Okay, now let us assume ky as a z. Again, let ky as a z. If y is 0, then z is 0. If infinity, then this is infinity. So same as, and this is here 0 to infinity, and differentiate k and dy and dz. Okay, so this is here 1 over k, and in place of dy, and that would be here and dz. Okay, and this is here y means z by k, so z by k and whole to the power n, and that is here z to the power n plus 1 and z to the power 2 plus 1, and this is equal to 1 over k to the power n plus 1 integral 0 to infinity z to the power n and dz, and this is here z to the power n plus 1 and z to the power 2 plus 1. See, this is here z to the power n plus 1, and this also z to the power n plus 1. So for we want to get here on the numerator part be z to the power n plus 1, so add by 1, and this is, and for balancing subtracted by 1, so this is z over dz over, this is z to the power n plus 1 and z square plus 1 here, and partially differentiate these two part here as a two integration, that is this over this is dz over z square plus 1 square minus 1 over k to the power n plus 1, and this is 0 to infinity, and also dz over that is z to the power n plus 1, and this is z square plus 1. Okay, and this is 0 to infinity. Okay, now see, and this is here I, but, and this is actually, this is 1 over 1 by k to the power n plus 1, and this is tan inverse z, and this is 0 to infinity, and this is, let us assume this is I1, so this is here I1. Okay, now again write I is equal to 0 to infinity dx over k square plus x square, and this is k square plus x to the power n. See, pattern is here z to the power n plus 1 and z to the power 2 plus 1. So now another substitution method here is, in place of x we put here let x is equal to k times of m. If we differentiate dx k times of dm, and the limit if 0, if x is 0 then m is also 0, if infinity then m is also infinity. Okay, and dx is equal to k times of dm, and this is here k square m square, and this is here actually k to the power n, k to the power n, k to the power n, and m to the power n. This is if we take common k square and k to the power n, and then power we have k to the power n plus 2, and here is numerator c k to the power 1, so the coefficient here is k to the power n plus 1, and this is 0 to infinity, and dm over this is m square plus 1 and m to the power n plus 1. And now apply the property here, like, and look here, same pattern, here is the same pattern, so you can write here 0 to infinity dz over z square plus 1 and j to the power n plus 1, and use the property here like 0 to, a to b, since a to b f of x and dx, it can be written as a to b f of z and dz. So this is as a I1, so I is equal to, this is as a I1. So from 1 from 1, and this is I equal to I1, this is 2, so from 1 and 2, then I is equal to, that is 1 over k to the power n plus 1. If we put the upper limit here infinity, then we got here pi by 2. Okay, and if we put 0, then is 0, so this is minus I, since I is equal to I1. Okay, so add by I plus I, this is 2I, so this is pi by 2 into 1 over k to the power n plus 1, so I is equal to pi by 4 into k to the power n plus 1. So this is your answer. Okay, see carefully, this is a very interesting problem, so all of you. So thank you for watching my video.